Welcome to Clark Classroom. Don't forget to subscribe. In this video, we look at the proof for the surface area of a sphere. As in our previous video, we turned to calculus to give us this proof. And I want to direct your attention to this diagram here that we have on the left. So, we will focus on just the top half, which is our hemisphere. And what we're doing here is slicing this hemisphere into approximate cylinders that you can see right there. Take the surface area of each cylinder and apply the rules of calculus to obtain our solution. We are interested in two key pieces of information. One, the radius of the cylinder. Trigonometry tells us that if this is the radius of the sphere, and we have here a right triangle, so this leg of the right triangle is going to be given by r times the sine of the angle theta. And the other piece of information that we are interested in is the approximate height of this cylinder, because the curved surface area of the cylinder is given by the radius and the height. So we have the curved surface area of the cylinder to be equal to 2 pi r h. Now I want you to recall that for the sector of a circle, the arc length is given by the product of the angle theta and its radius, where angle theta is measured in radians. Now we are interested in really thin slices of the hemisphere. And as we approach those really thin slices, let's examine the height h of the cylinder. Recall that for a sector with angle theta measured in radians, then the arc length is given by the product of the radius and the angle theta. So the arc length is equal to r theta. Now, as theta gets really small, we have a situation where the arc approximates the chord as theta gets really small, and we can now treat this arc as the height of our cylinder right there. When we apply the rules of calculus, it tells us that as delta theta approaches 0, then the limit now gives us the integral over the range of values for theta from 0 all the way down to pi over 2. So at 0, our r sine theta is 0. And when we get to pi over 2, our r sine theta will be equal to r. Over this interval, we are now looking at the integral of the curved surface area of each cylinder, where r is now represented in our integral by r sine theta. That's the radius of the slice of that cylinder. And the height h is represented by r times the small change in theta. And so that gives us 2 pi r squared. R times r gives us r squared sine theta, and that limit, as theta approaches 0, we now have delta theta. We can now move the constant 2 pi r squared to the outside of our integral, and we are now left with the integral from 0 to pi over 2 of sine theta d theta. And you will recall that the derivative of cos is negative sine, and therefore the integral of sine, the antiderivative, is going to be negative cosine of theta over the interval from 0 to pi over 2. And now when we plug in those values, the cosine of pi over 2 is 0. Remember that? And of the cosine at 0 is equal to 1. So we are subtracting a negative 1 in that interval. And so 0 subtract a negative 1 is going to give us positive 1 times 2 pi r squared gives us 2 pi r squared. Recall here that this result is the result that we obtained from moving through the angle 0 to pi over 2 for the hemisphere. So if we want the complete sphere, then we have to now multiply that result by 2 to give us the answer 4 pi r squared. If you find this video useful, please subscribe to this channel, and I welcome your comments and or suggestions.